Here we go. All right. We are talking about Chapter 18 with a title, The Size and Number of Stars. We have the HR diagram shown as our cover image with luminosity and temperature and some groupings of stars and their different colors. We'll talk about that quite a bit. Okay, so to get started, we're going to talk about something that you didn't see coming, binary stars. What's that? And even more, in a few slides, you're going to be asking yourself, wait, why are we talking about this? Why do I care about binary stars? So I want to hopefully motivate, why we are, just to start. And naturally, we'll come back to these ideas. The reason we care about binary stars is because they allow for measurement of mass and size of stars, which is a big deal. It's a big deal because those are important quantities. Think about when we talked about planets, we always wanted to know its mass and size. You can get density that way, right? This is going to be crucial for any sort of calculations that, think about physics equations. They always have, m for mass, r for radius, which is, size, right? So obviously we're going to care about that for gravitational strength, all kinds of things. So hopefully it seems totally obvious. We care about mass and size. But why do we need binary stars to do that? Because stars are just little dots. No matter how good your telescope, a star is just a dot. You can never see a star as a circle in a telescope. They're all too far away. So you can't just measure the angular size of a star. There's just no way. The resolution could never be good enough. Well, that's a big problem, right? Because that's just even for the closest stars. Some of them are so far away that it becomes even more of a total like zero chance of ever seeing them as more than just a single dot. They're incredibly bright, and we can see their color, and we already know that there's a wonderful and convenient connection between color and temperature. Cool. So we know temperature for free, essentially. We can look at the emission spectrum that happens in the surrounding atmosphere around that star. We know we can look at Doppler effects in order to know how what's going on with motion, and we'll come back to that. But then how do we get size and mass? Or yeah, really size and mass, right? Well, we get it when two stars orbit each other, because that allows for observations that, well, let us make these calculations and fill in those blanks. Turn those little dots into something with a value of mass and a known size. Okay, so binary stars are two stars that orbit around each other, so to speak. They orbit around a shared center of mass called the barycenter. So it's just a pair of stars. Our sun doesn't have, a twin, so to speak. It doesn't have another star that it's paired up with. So our solar system is not a binary star system, but many are. Our closest neighbor, the Alpha Centauri, is actually a three-star system. It's got three stars, but one is much further away, so it almost behaves like a binary star system. Okay, here's an example of two of them in the Albireo constellation, Albireo A and Albireo B. It's a binary star system. It's asking you which one is hotter, which is a review question with color, which I kind of like because as I said a second ago, it's the one thing we already know about stars. We know their temperature just by looking at their color. And I don't necessarily expect you to know like the values or anything, not yet at least, and you can always look it up, but hopefully we'll get to a point where you know where to look it up. But which one's hotter, right? Is it the blue or the yellow one? You know? So I won't check chat right now, but for your own, you know, knowledge and, confidence, you could put your answer there. Which one? Blue or yellow star? Which color corresponds to a hotter star? This is the one that doesn't have it. It's a blue one. The blue star is the hotter. Okay. Remember the black body radiation curve. Okay, so here is another image of a binary star. This one's just, we just see them side by side. But here's one where we're actually seeing them, kind of head on, and we're seeing evidence of their actual orbit. Okay, so I don't know if this was like how exactly what the photo's showing. It says infrared, and so it's probably showing some sort of a disk around them. So maybe these are young stars, and this is the protoplanetary disk, the early stage of a solar system or star system or planetary system, which they're often called. And like when we talked about planetismals and before the planets were fully formed. And so what's happening here is that that's actually showing up and really highlighting the fact that these stars are in this swirling motion with each other. So they're essentially like moving around each other, orbiting around that shared point in motion. Okay. Here's another example of a binary star system. Okay. And this example, I ended up kind of, people were asking a bunch of questions in the other section about it because they're like, whoa, what's going on here? Like there's a bunch of crazy stuff, this image is an X-ray image here on the left. And then on the right is just an artist's rendition of kind of what is going on if you had a perfect view of it. So to suffice to say, what is going on here is something we will talk about early next week. I don't think we'll get to it tomorrow, but it's a crucial step in like star evolution, essentially when stars start dying. In fact, in this case, this star, which is actually right here, and the disk around it, well, aren't even officially a star anymore. What this is called a white dwarf, which is the corpse of a star, and that dead star is feeding off of its still living brethren over here. It's pulling mass off of the maybe red giant star that it shares an orbit with. And this actually happens a lot, this process, okay? Which totally interesting, but not the main focus of why we're talking about binary stars right now. So kind of hold the idea for now. We'll come back to it. There are types of binary stars that we're going to discuss. And remember what I said about the reason we care about binary stars, at least at this point, because you could say, oh, you care about them because of these interesting interactions that happen, right? As one of the two of the binary system. Okay, bi means two, so two star system, binary system. So one of the two of the binary system dies first. Fascinating things happen. But we don't care right now, right? Right now, the way we want to separate and think about binary star systems is with the way we observe them. Because our whole motivation right now is just to establish measurements. It sounds kind of boring, right? But it's also like nothing will proceed until we know how to measure mass of stars and size of stars. So that's why we're going to be talking about, for example, a visual binary system. So it doesn't say at all what types of stars they are, whether they're blue or yellow or hot or cold or big or small. All that this definition, this name means is our view of the binary system. Okay? So a visual binary is a binary system where the two stars can be distinguished as separate objects in a picture or by eye. Okay? So, but the picture has to at least be taken, or by eye the eye has to be on the lens of a telescope. So it can't be naked eye, but you could be looking through a telescope. Okay, so for example, this is a binary star system with one really big star and one small one, right? You can see the little tiny one there. And so we'd say it's a visual binary because we can look head on and actually see the two dots for the two stars. And you might be thinking, hey, this isn't a dot. This is a big circular smudge. Well, it's a smudge, right? So all of the size here is just like resolution blurring. This doesn't actually relate in any way to the size of the star. From like going from this, from there to there. It's just a blurring effect because of the limitations of resolution. So there's no, by no means could you say, oh, look, I guess I'll measure from like, from, where the blur, where that blurry circle becomes particularly thick, and say, oh, this is the radius, and oh, it's a lot bigger than this other one. It's just a single dot, 1 pixel. That would be totally inaccurate. That it wouldn't give you anything to do with their actual size, right? Because we can't tell. And, the blur here is no different than the big kind of flare lines that come off to the sides. They're all just, limitations of the fact that, we're using lenses to get these images. Okay, so with this, visual binary system, we can, the center of mass is going to be kind of located somewhere directly in our line of sight. So we're looking at the star system from above is one way to think about it, or at least like in a way that the plane of their orbits, and this is the same as like we talked about the plane of the solar system. Remember, it's planar. The ecliptic plane was the name. Well, every solar system is essentially a flat plane, okay? And so you either look at it this way, which is like, where it's like a picture on the wall, or, the floor, and you're looking from above, and it's flat. Okay, so that's the idea. Visual observations are when you happen to have a view where you can look exactly at the motion as flat. So the center of mass could be right here, and we can see the stars orbiting around that shared center of mass. Okay. With these binary systems, there ends up being some interesting trends with size, which I'll just touch on because again, it's a idea that we can delve into quite a bit, but it's not going to get us any better understanding of the main idea of this section of this chapter. Okay, so first of all, I had said this a little bit, but it can't be stressed enough, is that binary stars are common. They are very common. The fact that our sun is by itself is not like rare, but it's like almost like, just like a 50-50 chance that it could have been with another star. It's totally probable to have binary systems. And this breaks down by size of one of the two stars in a binary system and the number of average companions that star has, and what the mass difference is between the two. So a lot of information here, a lot of, in fact, really cool, could be a discussion for hours to talk about this. What I will point out is that kind of if you look at stars that are mid-sized in general and a little bit bigger than the sun, so these are stars that have a mass from 1.5 to 5 m sun, where m sun is like a unit that we use, which is just a multiple of the mass of our sun. Okay, well, these stars that are a little bit bigger than our sun, when they tend to have so they have about a 50% chance of being in a binary system, and then the other star that they're with has about a 50% chance of being so the average percentage of mass in the larger star. So in fact, this one's not a chance. This is just dividing it up. So it's saying that the other star in the binary system, of which there's a 50% chance is there in the first place, is going to have about half of the mass. If that sentence seems a little complicated, what I'm just saying is that in this case, for this size range of stars, when they're in a binary system, they usually are the same size as each other because they both have, because this says average percent of mass in the larger star. Well, if the larger star has 55% of the mass, that means the smaller has 45%, which means they're pretty close in size. Okay, so that's in this range, these stars tend to pair up with other stars that are about as big. There are lots of cases where real small stars tend to actually pair up with really big stars. So there is a really common case of small stars, ones that are less than 1/10 of the mass of the sun, pairing up with another star that makes up 97% of the matter. So that means the small star is only 3%, the big one is 97%. So that's a totally lopsided relationship, almost like like a gas giant and a star, but also the almost being a bit of a stretch, because remember, Jupiter is less than 1/10 of 1%. Here, we're talking about 3%, so at least 30 times bigger than Jupiter. But still, real small star, real big star. That also tends to be a common pairing. Fascinating, right? Why exactly does it work that way? Probably because of physics. I don't know the exact mechanism, but real kind of, interesting data set. Why do we care? Mostly because we'll talk about kind of the consequences of these lopsided systems later. For now, just take it as, some interesting data that is going to hold your attention down the road. Okay, so far though, we've talked about a visual binary. That matters, for our current discussion. And that's the type of binary system where we can just see it head on. Oops. Well, let's get to the next type of binary star system, which is a spectroscopic binary. Again, does this name have anything to do with those size disparities or anything? No, right? Neither did the visual. It's all just about how we're seeing it. Okay, so what is a spectroscopic binary? Well, this is where the two stars can be distinguished from their spectral lines, not from direct visual observation. So we're going to see instead Doppler shifts that represent their motion either towards us as the observer or away from us, us being Earth. Okay, so review of the Doppler effect. We just saw it with helioseismology, so probably fresh in your mind. Stars A, B, and C are identical and emit blackbody radiation with the same peak wavelength. So we know that all these stars are the same type of star. The waves drawn are the peak wavelengths of the stars as seen from Earth. Okay, so we got green, blue, and red wavelengths. The wavelengths are shifted due to the motion of the stars. Okay, if star A is stationary, the one that's producing the green wave, kind of a mid-length wavelength, and which star has its light shifted to a longer wavelength? Well, if you look at it, it's obvious, right? It's the one that literally is more stretched out, right? So star C shifted to a longer wavelength. Okay, so if star C is moving, or is star C moving towards or away from Earth? This one, I'm going to check. Star C. We know it's the one shifted to longer wavelengths. So does that mean it's moving towards or away? All right. Nice. Thank you, Maxwell, Kaylee, Maria. You're all correct. The redshift. It seems like you are all getting that down. Remembering, redshift is motion away from us. So which is the spectrum for star C? Okay, so this is, okay, so below is the spectrum of star A. So this one corresponds to the star that's at rest. It's like the reference spectrum. Then we're given two options of spectra that have been shifted, and then we're asked which one must correspond to star C. The one that you just correctly identified is moving away from us. So which is it? The one on the top, which is thumbs up, or the bottom one, thumbs down. All right. Anybody else? I got one up. Okay. So the top one. Okay. You are both right. I think I saw just two answers. Am I missing? Yeah. All right. Absolutely. Because it shifted in the red direction. Okay. So it shifted this way. That's a red shift towards longer wavelengths. So excellent. You recognized what it looks like in the spectrograph. Okay. So the spectra are complex. They got a lot going on. They don't tend to look like these really clean ones. This example is usually like just pure hydrogen. Okay, but in reality, we got lots of different gases that have their absorption spectrum. right? There, that because that's generally what we'd be looking at too, would be absorption spectrum, basically the sunlight passing through something, usually the atmosphere of the star itself. Okay, both stars are moving, so we've got oscillation spectra. So, in other words, the spectra is going to be changing in a periodic way because, we have orbits after all, repeating motion. Different speeds because, sometimes the star will be moving directly towards us, sometimes towards us, but at an angle, and those are going to register as different amounts of shift, thus different velocities, because we can only measure the component of the velocity that either points straight towards us or straight away. All right. And then the whole system is going to be moving away, which is not a number we normally worry about, which is sort of like the relative motion between stars as the whole galaxy does its slow, or, dance, so to speak, its slow rotation. And, the galactic arms are sort of, they're oscillating up and down. And there's all this motion between stars. But when you're making really careful calculations, when you're measuring tiny changes in velocity, that motion between stars can matter, and so you would be looking for a constant that is on top of the oscillation motion. Okay, so from this data, from the spectroscopic binary, measurements of the orbit size and orbit time from the Doppler shifts tells us about the mass of the stars. So we finally got to what I pitched as the main idea, the main reason to care about this, is that this binary system and the measurement that's made with the spectroscope and knowledge of the Doppler effect can lead to a measurement, an indirect measurement, but a reliable one, for the mass of the stars. Okay? And it's going to be using Kepler's third law. I also wanted to point out that when we talked about visual binaries, if it seems like we just kind of mentioned them and moved on, they can be used for the same thing. They can also be used to calculate from orbital size and orbital time the mass of the star. In fact, in that case, you don't even have to worry about the Doppler effect because you can literally just see them moving. Okay? So they're almost the easiest to work with. This idea of using spectroscopic measurements to calculate the mass of something is also used to study and determine the mass of planets that orbit around stars. In that case, you're only looking at one oscillating spectral line, that caused by the planet, rather than two lines. And you look at the wobble that the planet induces on the star. Because you can't see the light reflected from the planet itself, it's way too dim relative to the starlight, of course. Okay, animation you can look at if you want to, go and follow the link. Okay, so what do we got so far? We've got a way, technically two ways, with visual binaries and spectroscopic binaries to actually determine the mass of a star. It lets us find the mass of both of them. And how would we do it? We go back and use Kepler's third law. Remember Kepler's third law with Newton's synthesis in it, right? So that's the calculation. So this is the only way that that we've talked about so far. There's a few others, but the really kind of the best way to determine the mass of a star. A star on its own, so a star that's not part of a binary system, would be like a black box to us. It'd be a mystery. We would not be able to use any easy approach like this, right? Relatively easy at least, to determine the mass of a star that is not part of a binary system. Once we know enough about stars, we can then kind of, say, hey, it's that type of star. It's the same as this other one, right? So the binary study is, something that happened historically and kind of just laid the groundwork of our understanding of stars. And it can continue to be done and refined, right? And data can be checked, but it does mean that we have such a big, catalog of stars now that when we find a star that, is on its own, we can still learn a lot about it by comparing it to all of our, known stars, because there's only really so many types of stars out there. All right, we'll be finishing in just a moment. Okay, so I haven't mentioned this graph yet. There's just kind of highlighting and summarizing what we've seen so far. What is this graph? Well, it is the mass luminosity relationship. So it's using our newly acquired quantity, mass, and relating it to luminosity, okay? And fun fact, we haven't actually talked about how we would know luminosity, which is the actual power output. We certainly know this for our own sun, okay? We can measure it directly, but can we measure luminosity directly for another star? Well, we can measure the apparent brightness and we can get luminosity from apparent brightness, but only if we know the distance. Ah, well, that's a whole can of worms. And basically the idea of chapter 19. So for now, just trust that there is a similar step-by-step explanation of how the heck we know distance, which is equally non-trivial and is a feat of logic and hard work over decades. That's astronomers know ways to actually measure the distance to stars because how do you, right? You can't just like, send a space probe out there. You certainly can't bounce a radar wave off a star because first of all, you'd have to wait many years and you couldn't really, get a good enough reflection. So there are ways. What we do have, if you remember parallax, that's one way. A correlation between radius and luminosity, okay? And then also there's going to be a correlation between mass and luminosity because we can relate it back to size. And then heavy stars tend to be larger. So we know that if there's a radius luminosity relationship, then we can also end up with a relationship between mass and luminosity. Okay. And interestingly, when they point this out, I wasn't even thinking of this, that mass correlates with both radius and luminosity. There's sort of like a theoretical idea too, that if we know the luminosity, we can use the Stefan-Boltzmann law and then say, okay, well then if we know the temperature, which we know from color, from Wien's law, you could then determine size directly from that. So, you could get size independent of a binary system if you already knew luminosity to high precision and you use those other laws to get there. So it's sort of like you kind of have like these different converging paths of measurement techniques. And it's fine. If some of that didn't make sense, what I just said, that's fine. Don't worry about it too much. Anyway, heavy stars tend to be more luminous, and that's what the graph is showing. Just to quickly call out the axes, we have luminosity on the vertical axis ranging from 0 to 1 million times as bright as the sun, because that's what luminosity means, brightness. And on the horizontal axis, mass, also measured in solar, but of course solar masses this time instead of solar brightnesses or solar luminosity, ranging from 0, so no mass at all, up to stars that are 20 times as massive as the sun. So we see that if you get just a little bit bigger, 10 times bigger, right, then you get a lot more bright, a lot more luminous. So 10 times bigger is about 10,000 times brighter. Right? So quite a dramatic relationship. Okay, so let's stop there. All right. We'll start with this check your understanding, which will be a great way to pick up where we left off. We'll finish off these slides tomorrow morning and take the quiz after we finish them. So expect the quiz to be right at the 1 hour point, but maybe a little bit earlier, maybe as early as 8:40, but no later than 9. Okay, so that's it for today.
Thank you. Have a nice day.
You too.